Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing unsteady flow simulation options. This is part two of a three videos on this topic of unsteady flow simulation options. So what I'm talking about here is I got my HEC RAS up. I'm going to go up to the Run menu, Unsteady Flow Analysis. This dialog box pops up here, and then in the Options dropdown, Part one was from stage and flow output locations down to the first tab of computation of options and tolerances here. This specifically the first tab. In this video, I'm going to be talking about all the remaining tabs from 2D flow options all the way down to 1D mixed flow options. And then in the third part, the next video, will be all the other options here, which is output options down to view runtime messages. All right, so let's go ahead and get started here with part two. This is the unsteady flow simulations. Click on options and now click on this computation options and tolerances. All right, so the second tab, which is where we're going to start, 2D flow options, has a number of different options here. I'm going to make this dialog box a little taller. There we go. And we start with this top checkbox here, which says use Coriolis effect, not used with the fusion wave equation. So if you check it off, Coriolis effect is not used. If you check it on, Coriolis effect is used. This takes into account the rotation of the Earth with your model computation. If you do check this to use Coriolis effect, you also need to insert the value on row 19, which is latitude for Coriolis. So just go ahead and type in a latitude here. Positive values represent northern hemisphere, negative values represent the southern hemisphere. All right, let's start working down the rows here. Theta and theta warmup values can range between 0.5 and 1.0. As you can tell, the default value here is 1, and this deals with the solution accuracy. 1 is more reliable, more stable, and less susceptible to instability. Perhaps a little bit less accurate, though. Probably shouldn't be too much less accurate, but 0.5 is more accurate, yet less stable. All right, row 3, the next one down is water surface tolerance. And I'm also going to throw in volume tolerance. These are two different tolerance terms that the 2D flow options account for when determining if the convergence criteria for the model has been met or not. So the maximum here is 0.2 feet, but the default is 0.01 feet. If the error from the model exceeds that tolerance of 0.01 feet or whatever the user provides, then another iteration of the model will be used. Unless the maximum number of iterations, row 5 here, has been set. So there is a default of 20 for the max iterations, and I think the max is 40. This first tab, general tab, says max iterations 0 to 40 here, but it doesn't say a maximum value for max iterations. All right, below that we have row 6, advanced convergence. These are, if you click this checkbox, you can now make some edits to a few other advanced convergence metrics, such as water surface max tolerance, water surface RMS tolerance, and then water surface stalling tolerance on a percentage basis. I'm going to go ahead and click that off, though. Row 10 is the equation set, and then this is actually a drop down. Yeah, so diffusion wave is the first option. And if you click the drop down, you have some shallow water equation options. SWE-ELM is Eulerian Lagrangian approach to solving for advection, and then just the EM leaves out Lagrange. It's just Euler's method. It's a stricter momentum, apparently. And then one last one here for local inertia. The user's manual goes into more detail about these different equation sets, so feel free to check that out. For instance, on SWE-EM, this method may require smaller time steps, which may produce longer run times. I would just go ahead and use diffusion wave, and diffusion wave will work fine for most flood applications. But you may want to set up separate plans in your model and then run the different plans with different equation sets and just see how that works. All right. Row 11, initial conditions time. And then I have that set to 10 hours. And then the next two is initial conditions ramp up fraction. And that's going to be a decimal between 0 and 1. That's going to be a fraction of the initial conditions time. These are used to reduce model instability. If the initial flow or stage is too high at the beginning of a simulation, then having this initial time and ramp up factor are used to prevent the instabilities. Boundary condition ramp up are based on a fraction of the initial condition ramp up time. So for instance, if we have a 10 here for initial condition time, see, can I make this wider? Oh, okay. Like this column doesn't need to be this wide. Oh, here we go. Oh, that's much better. Okay. Well, then I can't see all the tabs up here. Let's see. Okay, let's go right there. Okay, just resizing things here. Oops. And then boom, that's a little better. Okay, so anyway, if zero point 0.5 is my fraction, then 50% of 10 hours is 5 hours. If it was 0 0.2, then that 20% of 10 hours would be 2 hours and so on. Number of time slices, this is an integer value. And I believe they want a positive integer here. This option allows the user to set a computational time step for a 2D area that is a fraction of the overall unsteady flow computation interval. So remember, this tab that we're on is 2D flow options. So what that means is perhaps more detail and smaller computation intervals need to be used for 2D flow areas. And you can set that right here. What this integer is going to do is divide the simulation computation interval by this integer. So you may need to kind of think about what is the simulation computation interval. And in this case, let's see, I move this to the side. It is 1 minute. So for instance, if I wanted to have a 10-second computation interval for my 2D flow areas, then I would set this to, what did I say, 10 seconds. So this would be a 6. If I want it to be 6 seconds, this could be a 10 right here. If you just leave it at 1, it'll divide by 1 so that it'll be turned off basically. It'll just use the same computation, a time interval as the simulation itself. The next row down is turbulence model. Our options here are none, conservative, and non-conservative. So if you go ahead and select one of those, there are a few more parameters down here, 15, 16, and 17 for longitudinal mixing coefficient, transverse mixing coefficient, and this Magorinsky coefficient. The HEC RAS hydraulic reference manual provides more information on these coefficients and what they mean, and the user manual does not. So I'm just going to go ahead and refer you guys to the HEC RAS hydraulic reference model manual for more information on rows 14 through 17. Okay, row number 18, we have boundary condition volume check. So if we check this on, and I'm going to check it on, this option is used to prevent volume errors that may arise when 1D connections are made to 2D flow areas, such as when a lateral structure is connected as a 1D river to a 2D flow area. I don't see anything wrong with that unless it's really slowing down the computation. All right, after that, we have the latitude for Coriolis. We already talked about that. Row 20 here is solver cores. I have it set to all available. I believe this is a drop down. Yep. So my computer has 1 through 64 cores available. Your computer may be a little bit different, but for the most part, the larger, more complex the computations, then the more cores used will solve it a little bit faster, is how I understand that. So if it's a very simple model, you may not need to use all your cores. In fact, more cores may actually solve the problem a little bit slower. I'm just going to leave it at all available right there, though. And then row 21, matrix solver. Our options are in a drop-down, Paradiso, SOAR, FGM, RES, SOAR. These are two iterative approaches. The original method and the recommended method here is Paradiso. I don't know if I'm saying that right. I'm just going to call it Paradiso. And I would go ahead and use that. It'll probably work the best anyway. But if you suspect that one of these other methods will work better, I would probably recommend you setting up a plan for each matrix solver and then testing it, because there's a chance that one of these iterative methods could solve for convergence faster than the direct method. All right, rows 22 through 27 are not mentioned in the user's manual, at least not in this section. I'm going to link to the user's manual for the page that discusses this entire text box here, all the tabs, but these last few rows were not mentioned. All right, let's go ahead and move on to the next tab. We're on to pipe systems. And the user manual also does not mention anything about pipes, this particular tab. It just moves on to the next tab. But there are some clues about pipe systems in other places of the user's manual. I just don't want to commit to saying that it's related. All right, next tab over is 1D and 2D options. So if you want to turn this value off, this option off, it's 0 for the first field. So it's currently turned off. It's turned off by default. But if you want to turn this feature on, then you would insert a number between 1 and 20 inclusive in this first field, and that would represent the maximum number of iterations between 1D and 2D. So for instance, you have a 1D channel, it's connected to a 2D flow area via a lateral structure, then those initial flow calculations need to be determined. And this tab will help facilitate that. Most 1D and 2D connections will not need iterations. However, when during submerged conditions, then iterating might be necessary to get a stable answer. So I'm going to go ahead and just leave this on. There are a few criteria here to specify as well. For instance, the water surface tolerance. If the air exceeds the user specified tolerance, then the next iteration will occur unless you've already hit the maximum number of iterations. And then the next two fields sort of work together. That's flow tolerance on a percentage, as well as minimum flow tolerance in a flow rate. So the way that works is if the air exceeds the flow tolerance on a percentage basis, it will repeat to the next iteration unless the overall flow is less than this minimum tolerance. So if the flow is very small, it's almost negligible. However, you could still suffer from a large flow tolerance percentage error, even if you have a very small flow rate in CFS. Alrighty, on to the next tab. It's advanced time control. And I've already been clicking around and adding some data in here to kind of learn how it works. But we have three methods here. First is the fixed time step. This is the basic method. This is the method that is default and would defer down to this computation interval here of 1 minute on the main screen for unsteady flow analysis. But for instance, if you wanted to adjust that time step based on the current number or on the time series of divisors it's called, you would check either this second radio button or the third radio button on this advanced time step control tab. All right, so just a quick introduction on how that works. If you click on the adjust time step based on the current number, what you need to specify is the maximum current number, the minimum current number, and then a few other parameters. Right now, I've set the current number to 1. This is the maximum current number allowed in any 2D cell or 1D cross section. If the maximum current number is exceeded, then the time step is cut in half for the very next time interval. The current number should be most 1 for explicit methods to maintain stability. However, HEC RAS uses an implicit method which allows for the current number to be greater than 1 in some situations. So you may have a number the user manual says as high as 5, but it should be probably 1 is good to be safe. Also, the minimum current number must be less than half of the maximum, or you could say it the other way, the maximum must be more than twice the minimum. This minimum value here I've set to 0.45. This is the minimum threshold for 2D cells and 1D cross sections. If the current number at all locations goes below this minimum value right here, then the time step will be doubled. The number of steps below minimum before doubling is right here. So it's set to 4, which means it needs to be below 0.45 4 times in a row before it will actually double. And then the next two fields down here is the maximum number of doubling time steps. So right now it says, let me see, the computation interval is 1 minute. So 1 minute, if you double that, that would be 2 minutes. That's 120 seconds. So 1 right there. So this means I doubled it once, it would be up to 120 seconds. If I doubled it 2 times, it'd be up to 240 seconds. So it gives you a little preview if you have trouble multiplying, 1 times 2. Then you can see what that is in seconds. In a similar situation happening here, if the maximum is exceeded and you need to half the time step, then again, if you halved 60 seconds one time, it would be 30 seconds. If you halved 60 seconds 2 times, you'd be down to 4 15-second intervals and so on. There's also this box for current methodologies, and the first radio button is selected by default. This is recommended. And what it is it calculates that current number as the velocity divided by the length, specifically the velocity times the dt dx. Yeah, dt and then dx, where this dx, the cell to the distance, is going to be, for 1D, it's going to be the distance between that cross section and the next downstream cross section. And then for 2D flow, it's going to be the distance between the two cell centers. There's also an option here for residence time. This is another current methodology. This only applies to 2D flow areas, though. So even if it's selected, then 1D flow areas will use this first equation. So that's how to adjust the time step based on the current. But if you want to adjust it based on time series of divisors, this table actually started off blank when I first opened this tab, but I've typed in some date times here as well as divisors. So it's important when using this option that the date time starts at the same date time as your simulation, which for me, it currently doesn't. So I'm using Jan 1. Let me go ahead and change that. So this is the date time. I'll copy that. Options, computations, and then let's see, we're on this right here. Let me just paste that in. Okay. All right. So I've matched the start date time of January 1, 2025 at 0, hours. That's the start date time of the simulation. So we're good there. We have a computation interval of 1 minute. So the divisors are going to be dividing that 1 minute by whatever value we type in here. So if I said 5, then 60 divided by 5 is 12 seconds. 60 divided by 4 is 15 seconds. 60 seconds divided by 2 is my 30 seconds, and so on. So this time step column is the calculated quotient of the computational time interval divided by the user supplied divisor. Let's go ahead and move on to our final tab here for unsteady computation options and tolerances. What this is 1D mixed flow options. This option should only be selected if you have a mixed flow regime situation, such as subcritical flow up to down to supercritical flow, or the opposite where you have a hydraulic jump from super to sub. When this option is turned on, like right there, the program monitors the Froude number at all cross-section locations at each time step. Not a lot of discussion on this particular tab in the user's manual. It tells the user to reference the user's manual in chapter 14 for more information. All right, well, that was it for this lesson 2 out of 3 regarding the unsteady flow simulation options. What we did was we went to the options tab, computation options and tolerances, and talked about all of the tabs here except the first one. General is covered in part 1, but we talked about in brief the 2D flow options tab all the way through 1D mixed flow options.